Hello and welcome to BT Productions. My name's Tyler.
And I'm Bilal.
Today we are here at Nashua Access Fieldhouse on the north side of Fredericton. We'll be doing a momentum impulse demonstration with one of our favorite sports,
Badminton.
We're going to have slow-mo, lots of slow-mo shots. We're going to be talking about the science. There's going to be a lot of cool, epic badminton smashes, drop shots, clears, all that. Hope you guys enjoy.
In our first experiment, the mass of the shuttle and racket don't change, therefore the mass m remains the same between trials. The speed of swing doesn't change, therefore the force F remains the same as well. These are our constants in this first experiment. Our independent variable in this experiment was the time, t, that the racket was applying a force onto the shuttle, which we controlled by either following through or not following through after hitting the clears. Throughout all three experiments, our dependent variable was the change in velocity, delta v, which we observed from the distance our shuttle traveled. Why does the distance represent the change in velocity of our shuttle, you may ask? Well, the initial velocity of the shuttle before it is hit by the racket is roughly the same no matter how hard the shuttle was initially hit. By counting the number of frames and using various objects in the frame, which we know the length of as a reference measuring stick, we calculated the average shuttle speed before being hit to roughly 7 meters per second with an error of about 1.5 meters per second. Therefore, because the initial velocity remains about the same, the final velocity and the change in velocity are directly proportional, with the final velocity being equal to the change in velocity minus 7 meters per second. Knowing this, if we have a higher change in velocity, then our shuttle will have a higher final velocity after being hit. And since the time it takes for the shuttle to fall to the ground will always remain the same, as long as I hit the shuttle straight forward, the horizontal velocity will be the only factor affecting how far the shuttle travels horizontally. If that doesn't make any sense, don't worry, just keep in mind that a farther shuttle means a higher change in velocity, and vice versa. We ran two trials. In the first one, the racket hits the shuttle and stops. In other words, there was no follow-through. This meant that the time the shuttle and racket were in contact was shorter. T, therefore, is smaller. This short contact time resulted in the shuttle to travel only half the length of the court, approximately 7 meters, which from what we deduced previously means it had a smaller change in velocity. In the second trial, the racket hits the shuttle and continues the swing. In other words, there was follow-through. This means the time the shuttle and racket were in contact was longer. T, therefore, this time is larger. This longer contact time resulted in the shuttle to travel almost the full length of the court, approximately 13 meters, meaning it had a higher change in velocity. Now yes, you could say that because I hit the shuttle slightly upwards in my clear with a follow-through, that could have been why it traveled further. Therefore, in order to confirm our results, we decided to use our frame measuring technique again to verify the shuttle's speed between trials. We found that with a follow-through, the shuttle's velocity was roughly 75 meters per second, whereas without a follow-through, the shuttle's speed was only 22 meters per second, about 3 times less. Of course, this isn't a scientifically rigorous experiment, but we only need to see how our dependent variable changes relative to our independent variable. And this first experiment showed us that when the force of the racket and the mass of the objects remain constant, a longer time of contact will result in a higher change in velocity. So, on to our next experiment.
In our second experiment, the mass of the shuttle and racket again do not change. Therefore, the mass m remains the same between trials. However, instead of swing speed, time of contact is now a constant in this experiment, which we attempted to keep the same throughout trials by always following through with our shots. These are our constants in this second experiment. The speed of swing does change now, meaning the force F is the independent variable in this experiment. And as we mentioned before, the dependent variable was the change in velocity, delta v, which we observed from the distance our shuttle traveled. Now you might be wondering how changing the speed of the racket affects the net force on the shuttle, but allow me to explain. Let's say you have a 0.5 kilogram racket traveling at 50 meters per second. It hits the shuttle and slows to a speed of 45 meters per second in a time of 20 milliseconds. Its acceleration is therefore negative 250 meters per second squared. Multiplying that by the mass of the racket, which is 0.5 kilograms, gives you negative 125 newtons. And negative 125 newtons is the force which the shuttle applies onto the racket, according to Newton's second law. And according to Newton's third law, the racket must also apply an equal and opposite amount of force onto the shuttle, so positive 125 newtons. In other words, the faster the racket, the more acceleration it has, and the more acceleration it has, the more force the shuttle applies onto the racket. And the more force the shuttle applies onto the racket, the more force the racket applies onto the shuttle, resulting in a larger force, F. Again, we ran two trials. In the first one, the racket hit the shuttle at a slower speed. And as we mentioned before, this meant that the force the racket applied on the shuttle was less. This smaller force resulted in the shuttle to only travel half the length of the court, approximately 7 meters, which makes sense according to the impulse momentum theorem, stating that a smaller force should result in a smaller change in velocity. In the second trial, the racket hit the shuttle at a faster speed, and as we mentioned before, this meant that the force the racket applied on the shuttle was larger. This larger applied force resulted in the shuttle to travel almost the full length of the court, approximately 13 meters, meaning it had a higher change of velocity, which again makes sense according to the impulse momentum theorem, stating that a larger force should result in a larger change in velocity. In order to further confirm our results, we decided to use our frame measuring technique again to verify the shuttle's speed between trials, and we found that with a fast swing, the shuttle's velocity was roughly 70 to 75 meters per second, whereas a slow swing launched the shuttle at about 9.4 meters per second, a lot slower. A very fast speed, such as a smash, launched the shuttle upwards of 80 meters per second. And again, this isn't a scientifically rigorous experiment, but we only need to see how our dependent variable changes relative to our independent variable. And the second experiment showed us that when the mass of the objects and the time of contact remain relatively constant, a larger force applied onto the shuttle will result in a higher change in velocity, again demonstrating the impulse momentum theorem. On to the next experiment. Third and final experiment, we kept our force and time constant, as you can see by the racket's speed and motion being roughly the same between trials.
The mass of the shuttle, however, is now our independent variable, and we controlled it by using either a regular 5.5 gram badminton shuttle or a 25 gram miniature tennis ball, with about the same elasticity as the shuttle's tip. Our dependent variable was still the change in velocity, delta v, which we observed from the distance our shuttle traveled. We again ran 2 trials. In the first trial, we used the lighter badminton shuttle and found that the average change in velocity after each impact was 11.5 meters per second. In the second trial, we used the heavier miniature tennis ball and found that its average change in velocity after each impact was 6.3 meters per second. This means that the object with the smaller mass, the shuttle, in fact had a larger change in velocity, on top of the fact that the shuttle had feathers, which should have slowed it down. And this is further supported by the impulse momentum theorem, which states that mass and change in velocity are inversely proportional. When one goes up, the other must go down if everything else is constant.
Okay, so that brings us to the conclusion of today's experiment. Today we looked at the momentum impulse theorem using the amazing sport of badminton. We went through the science, we looked at the momentum impulse theory and how it relates to sport of badminton and all the shots, clears, drops, and smashes. We learned a lot about momentum impulse.
And we hope you did as well.
This is BT Productions, signing out.